You're listening to Within Tolerance, a podcast for machinists by a machinist. I'm your host, Dylan Jackson from Proteum Machining, and this week I am rejoined by Adam Balogh. Welcome, Adam.
Hello, Dylan. Thank you for having me back. It's been like a year and some change since we did the first episode, so I'm really happy to be back.
Likewise. So for anybody who missed your first episode, you were on episode 90. And then why don't you give them a quick 30,000 foot overview of who you are, what you do, and then we can get into all the crazy stuff you've been into in the last year.
Yeah, so my name is Adam Balogh. I am an instructor in and the chair of the Machine Technology Department at Laney College in Oakland, California. I run our Instagram account, which is at Laney Machine Tech, Laney. I also have two YouTube channels, the Machine Tech video blog, and then there's also Laney Machine Tech, which has some like curriculum projects and stuff like that on there. I don't post that much to those two YouTube accounts, but they're there and there's some good stuff on there. So yeah, in my day-to-day life, I instruct future machinists, train future machinists. It's a very rewarding and sometimes exhausting job, but it's what I love to do. And, we'll get into, I'm sure soon here, like some of the really exciting things that are happening in our department. And especially this semester, there's some cool deals going on.
Definitely. Well, yeah, before we get into that stuff, I just want to thank you for being who you are. I know I went to my local community college. People have heard me talk about it a million times on the show, but it was such a formative experience for me. And especially one of my teachers, Jay, who really had such a passion very similar to yours, where like it just, he at the time he was actually an adjunct and working in a shop, and really opened my eyes to like how cool all this could be. And I went from saying like, oh, I'll just get my manual machining certificate, and I was like, oh, I'll take the G code class and see where it goes. And like once I'd started that taste, it really just changed my life. And so I really appreciate you doing what you do and really encouraging people to pursue what I think is like such a rewarding vocation.
Yeah, absolutely, man. Thank you. I appreciate that. It's the enthusiasm of a teacher can make or break someone's interest in an entire subject, right? Like if you have I've had a string of really bad math teachers, so that's probably why I don't really like math and never wanted to become, never wanted to go into math. But I had some very passionate machining instructors, and so that must have been a big reason why I got into it. And so to be able to be that person for other people is super rewarding.
Definitely. Well, actually, this might be a great time in the show, both for audience retention and to plug what is going on at Laney this next semester. I want to start it off right at the top. I know we had some questions about, what's going on. So why don't you tell us what the amazing things that are happening at Laney this next semester are?
Well, the really big thing is our Fall is Free campaign. So what it means, I mean, it's on the face of it, right? I mean, if you want to take classes at Laney College this fall semester, your tuition and fees, but also your textbooks are free. And we never had any lab fees or, you never had to buy your own materials or tooling or anything like that. So that's all free too, but it was always free. But basically, the only thing that it would cost you to take classes this semester in the machine technology department or any other department is your time. That's really all it costs you. And I guess gas money, which is pretty significant nowadays. So yeah, go ahead.
Well, I was going to say, so one of the questions we got from Murph's Machine was how is this even possible? I mean, it sounds amazing. And I really wish that more colleges would do this, or community colleges or whatever, but how is that even possible?
So this is really the best idea that our administration has ever had. What happens is, the last couple of years, because of COVID, all public schools have gotten some relief money. And last year they spent that money on, some like technology upgrades, which are they were useful, but they weren't nearly as useful as what they decided to do this semester, which is basically to give that money back to the students to help defray the costs of enrollment. So, this money didn't appear magically, right? I mean, this is taxpayer money, but that was going back into the schools to help, offset the effects of COVID. And I think that, because enrollment has been negatively affected by COVID across the board, but especially in community colleges and especially in career technical education departments, this is a major power play. And I think it's an awesome idea. I wish that we would keep it going because, to be honest with you, education used to be free in the United States, and especially in California, where we have something that was developed in the 1950s called the California Master Plan for Education, which said that there can be no tuition. So actually, no public institution in all of California can charge you tuition. So where these enormous costs are coming from, because at University of California universities and Cal State universities, the costs have been steadily increasing, and this is all in quote unquote fees. So basically, your enrollment fees are now your tuition. So it's a little bit of a sleight of hand there. But
Oh,
back in the day, it was free, and that's the way that it should be, because student debt is really it's like the only kind of debt that has a negative effect on the growth of the economy, because what you have is you have these people who are at the very beginning of their productive careers whose purchasing power is already severely limited. So it's a really negative thing. So it's very important to the health of our nation, I would say, the health of our economy, that education is accessible and inexpensive or free for all. I believe in that very strongly. At the community college level, in California at least, it's not like it was expensive. I mean, it was like $46 a unit, and a typical class is like 3 to 5 units. So that's not that big of a deal. But it's something. So to have that, offset, especially textbooks can be a major, major cost. So to have that offset is awesome.
yeah, that's amazing. I think New Mexico just made all community colleges free again, very
Oh, wow.
recently. And so, yeah, I'm a big proponent of that as well.
Yeah, I would be very surprised if people were against funding machining education in particular, right? I mean, our economy right now is in such a bad place when it comes to manufacturing. We have such a deficit of skilled workers that even if we wanted to bring all of this work back to the US, and we do, right? The biggest impediment, according to all of the companies out there, the biggest impediment to their growth is the lack of skilled workers. And it's only getting worse, right? Because all the stuff that we've been saying for the last 10, 15 years about, all these boomers and the people directly after them are going to be retiring. We were
Right.
saying that for a while, and now it's actually happening. So really, we should have been putting in this effort 10 years ago.
Oh,
Some of
yeah.
us were. But, better late than never. And so the more we can incentivize people getting into manufacturing, the healthier our economy is going to be. So I would be very
Definitely.
surprised if people were against it.
Completely agree. Murph's Machine's other question was, what class would you recommend for free this fall? Or classes?
So we have an introductory machining class, Machining 210. It's a manual machining class, right? This is our sort of gateway into the department. So you don't have to have any background in order to be successful in that class. But also, if you do have some background, like even people who've been working as machinists in a shop for a year or two, would still hugely benefit from taking that class because we really drill down on fundamentals. So we go through safety, how to read a blueprint, how to use precision measuring tools. We go through manual lathe, manual mill, drill press, tool grinding. So really broad spectrum, and we go surprisingly deep into each of those subjects. And we're a project-based curriculum for the most part. So even though we do have lectures, those lectures are really just preparation for the labs where you will be completing real projects. And it's not like they're not like just making a hammer or whatever, right? It's not just like some little thing like that. These are based off of real industry parts, and we hold you to pretty tight tolerances right off the bat. So, like on the first lathe project, you're using 4 high speed steel tools that you ground yourself to make the whole project. And we're holding you to standard thread tolerances. You make 2 threads, groove diameters that have to be +0, -5 thou. And then on the milling machine project, you're holding flatness, parallelism, perpendicularity of these surfaces on a sort of like an, L bracket, an angle plate of 1/1000th of an inch. So we're teaching you GD&T right from the get go. And holding 1/1000th of an inch on all of those on a Bridgeport is not that easy, right? So those are serious skills that you develop that you may not get if you're just cranking out parts in a job shop.
Yeah, definitely. I still have the pieces that I made for our first project in my schooling. We made a parallel clamp. And so on the lathe, you made 2 screws with groove diameters and everything. And then on the mills, you made the actual jaws, and then we ground them. And it's super cool. And actually, my business partner now and I were the 2, I guess, closest to nominal in the entire
Mhm.
class. And he beat me by like 1 thou on one dimension and loves to rub it in to this day of like, yeah, you're a good machinist, but like I'm 1 thou better than you.
Yeah, you'll
But
never live that down.
oh no, for sure not, for sure not.
So
Let's
that would be one class that I recommend. The other one would be machining 207, which is our mechanical drives class. That's a class that I designed myself and even created all these really detailed PowerPoint presentation slides and made like all of the solid models for all of the graphics in it. It was a ridiculous amount of work, but that was my favorite class that I ever taught when I taught it the first time. I had a really good group and they were very, they're giving a lot of feedback for the course. So by the end of the first time, it was an even better course than it was to begin with. And we're teaching that class also this fall. The prerequisite for most classes is machining 210, the introductory class. But if somebody wants to take that class and they have like a little bit of background experience, I'm happy to waive that prerequisite for them so that they can take the mechanical drives class. And in that class, we go over so many things. A little bit about the physics of power transmission. We go into bearings, so rolling element bearings, hydrodynamic bearings. We even talk about like hydrostatic bearings, air bearings a little bit. We talk about lubrication. We talk about various different drive types, belt drives, chain drives, gear drives. We also talk about motors a little bit and couplings between motors and other pieces of equipment. We talk about shaft alignment. And so we even have a laser shaft aligner that we let people practice on. And then we even talk about balancing, so static and dynamic balancing. I made a dynamic balancer back in the day because we didn't have enough money to buy one. And so we use that to demonstrate dynamic balancing principles. So those are the kinds of things that we're doing. And it's, again, very practical. So the labs have you actually doing work, taking apart gearboxes. For lubrication, we go into the machine shop and we go through all the machines and talk about lubrication and do some lubrication. So it's a really, really great class that I can highly recommend for people.
That's great. That sounds like a really unique class too. I don't know that I've seen that in a lot of machine tool curriculums.
Yeah, so we have 2 sides of our house basically. We have the manufacturing side, which is all machining, and then we have the industrial maintenance side. And so this is like an industrial maintenance class, but I think that even people who are interested in machining would find that class very useful because this helps you understand the machines themselves. And we do talk a little bit about, well, we kind of have a ready-made lab space for that class, which is the machine shop next door, right? So for a lot of our examples, we go in and check out the machines that we have in the shop, right? So when we start talking about linear motion, various different kinds of guideway configurations, linear guide rails, we talk about ball screws and linear motors and things like that, we head into the machine shop and take stuff apart and check it out. So it will really help you to understand the machine. And if you own your own business, or if you want to be that person in the shop who knows how to fix things, that's a good class.
That's great. That is super cool. Well, you mentioned machinery. Let's talk about the machinery you've acquired since the last time we talked, too. I think that I can't remember if it was on the podcast or just after we finished wrapping, you were talking about receiving your UMC. And I think you've received quite a bit since then as well.
Yes, it's so funny because I was looking back at that episode just the other day, and I was talking about the UMC 500, and that was, yeah, a year and some change, and we just got it like 3 months ago or whatever. So I mean, it was really, it's so hard sometimes to buy things in a, in a public institution. I mean, it should be hard because you don't want people spending money frivolously. But in any case, we got it. It's in. I was so excited about it. And this is part of a major shop. It's like a reorganization. I want to say it's like a modernization project. So we have traditionally been sort of a manual shop, and the manual part of our shop is still very much alive. Those skills are still in demand in R&D prototyping, in industrial maintenance type shops. But, obviously in production machining, CNC is the way to go. And so before we had only 5 CNC machines. And as of right now, we've got 9. And there are 2 more on the way. So by the end of the fall semester, we should have 11 CNC machines, which is the maximum that I can fit into our shop. But that's great because that basically means 1 machine per student, right? So that everything is about getting students more hands-on time with the machines, as well as increasing our capacities and our capabilities. So yeah, like over the course of the last year, it's been something like $1 million that has come into our shop. And a lot of that is coming from state grants. Like there's something called the Strong Workforce Program that has been supporting us, although that money is sort of fizzling out. But it's really for investment in technology and equipment to build up and modernize career technical education departments. So we've been buying CNC machines with that money for, I don't know, like 6 years or something. And because of COVID, like a lot of those purchases got sidelined. And so the last year, basically 3 years worth of purchases came through the door, which is why
Oh,
so much money
jeez.
came in. Yeah. So the UMC 500 is in. For those of you who don't know, that's a standalone 5-axis machine. It's a Haas. It's a really neat little machine. We'll probably end up running it as like a basic 3-axis machine just to increase our capacity. But then also we're working on curriculum for multi-axis machining. So that would be 5-axis, 4-axis, positioning, simultaneous, and we would add some other stuff to that as well, because the other machine that we just got, I think only a month ago, was a Haas ST10Y. So this is a small lathe, small turning center that has live tooling and C and Y axis control. So it's like a little horizontal mill as well as a turning center. We're also really excited about that because that broadens our capabilities dramatically. So between those 2 machines, we can do a lot. And we actually already have some 5-axis capabilities. So our 2 Haas VF2s have the TRT 100 tilting rotary tables on them, right? So those are small attachments, but you can do real 5-axis machining on them. The torque on the, now I can't remember which axis it is, but the table rotary axis it's pretty gutless, so you can't do like real hogging work on it. But
Right.
but that's not what we're doing anyway. So we've got those already, and then of course there's the Kern, and the Kern it's a 3-axis machine, but it has again a tilting rotary table on it. So we do now have 4 machines capable of 5-axis. So that's pretty cool.
That's amazing. So
It,
maybe let's talk a little bit about the Kern and how you got that and what that means for the department, because that's a pretty amazing acquisition.
it's one of the coolest things that's ever happened in my life. I'm so happy about it. And the story behind it is part of the reason why I love it so much. So it was actually on the day that the UMC 500 was being delivered, I get a call from Tony, who is the US sales manager, US manager of operations for Kern. And he said, "Hey, do you want a Kern machine?" Immediately, I said yes without even thinking about it, and then asked for more details, right? Because you don't say no to something like that. You say yes immediately because maybe it's just a dream and you want to make sure before the bubble is popped that it actually happened. Um, so the story behind this thing is that it's coming from a medical device manufacturer. It's actually a research shop, Alcon Research in Texas. I think they have a number of different shops around. And I think they were making some kind of inner ear implant on that machine. I can't remember exactly, but it had done it, or it had had its maintenance done by Kern just like a year and a half ago, and it checked out. I mean, it's a 20-year-old machine. It's a 2002 model MMP. So it's an older machine. This was basically the precursor to their Evo. So if the Evo is still a machine that they sell. This is like 2 generations before the Evo, but it's very, very similar in its design. It has essentially the same like guideway system, basically the same footprint and design. Anyway, so this is a 2002 machine. They didn't need it anymore. I think they needed the space more than they needed the machine. So they said, we're getting rid of it. And they told Kern that they were going to trash it or Kern could have it back. And so this is a machine that Kern, I think, didn't think that they could really sell because it's, back in the day, they were only making like 20 machines a year, something like that. I mean, a very, very low, limited quantity. So each machine was sort of custom built, even though they had models. So this machine was a little bit too purpose built for reselling to like a modern manufacturing facility. So Tony he's a friend of the department. He comes around, whenever he's in the Bay Area, and we've got, we have great conversations. He usually brings something interesting for show and tell. And I realized immediately that he and I see very much eye to eye when it comes to what it takes to revitalize manufacturing in the US. And from the very beginning, he wanted to find ways to help support us. And so when this machine came, to his doorstep, he immediately thought, I know who exactly could use this. And so he gave me the call. And they donated everything. They paid for freight shipping. Actually, the freight shipping and crating was done by another company that they deal with pretty frequently. I think it's their primary freight company that they deal with, logistics company. I'm really sorry, I cannot remember what it is right now, but hopefully we can put it in the show notes or something like that.
Yeah, definitely.
Because I really want to give them a shout out because they heard about what Kern was doing and they decided to donate their time, the time of the driver. So that came to us for free. The installation, setup, calibration, all of that was free. Tony himself came out to do training and do all of that. And then the machine has some really cool features. It's got this Bloom laser tool setter. It has that Hoffman tilting rotary table, and it's got some really cool features like that. But the one thing that it doesn't have is a spindle probe. So Tony was like, hold on a second. So he calls up the US manager of Heimer and says, hey, would you be willing to donate one of these, the 3D tasters, the little analog spindle probes?
Yeah.
And they said, sure. And boom, that was on its way to our department.
Oh, that's
So
wonderful.
everything about this was donated. It's like a gift to our students. And man, it's hard for me to even describe how that makes me feel because the work that we do in the department, I think, is really important. And it's hard work. Sometimes it's thankless. We don't get a lot of support from outside of like our department or outside of our division. Our dean is actually really awesome. But in general, we don't get a whole lot of support. And so for someone in industry to see what we're doing and then to want to support that in such a big way, it's so validating. And I really cannot say thank you enough to Heimer, to Kern, to the logistics company, and to Tony specifically for helping support us in that way. This is a huge deal for our students. It's a huge deal for the department. It's not just a fancy machine. It opens up a lot of opportunities for us because now we can teach high precision micro machining. We've got a Heidenhain control, which means we can teach that. We can demonstrate things like the laser tool setter. And I can even potentially develop curriculum around, ultra precision micro machining, which is something that I have been wanting to get into for a while. It's not something I personally have a big background in, but if you follow the Instagram account, you see that like that's where my interests tend toward. Um, so through very close contact with people in industry, I think that we can develop some curriculum in that area. And that would open up more opportunities for our students to get into those very high skilled, very high paying careers. And in the Bay Area, especially, we've got a lot of that type of stuff. We've got semiconductor that's down in the South Bay. We have medical device manufacturing that's sort of all over the Bay Area. We have several national laboratories that are around us, and they're doing precision work like that. There's also Zygo that's doing optical work in Richmond. So there are a lot of places around here where, and now students could get access to that. So that's really exciting.
Yeah, that'd be amazing. I know I see what Josh at NH Micro is doing all the time. And like some of those things I've had such limited exposure to. Like he posted just a little, it looked like a square on top of a piece the other day, and it was some kind of optical thing. And I was like, how do you even measure that without destroying the optical finish? And like there's so many little tricks and things like that that go into that that make it such a unique subset of machining. And so being able to do that, I think would be amazing.
Yeah, I love watching the stuff that Josh is doing, because it's not. I mean, the stuff that they do on their watches is amazing, but then for them to have been able to transition into doing sort of like commercial micro machining work is, I mean, it's like a natural progression. Like it's weird because watchmaking it's sort of like the original precision machining, right? The
Oh
original
yeah,
micro machining. So much of that industry comes out of watchmaking, to the point where, we'll talk about in a moment, the internship that I did just recently in Target Fabrication at Lawrence Livermore National Laboratory. Like they're using watchmaker machines to do some of this work for scientific research. Like they're a big fan of Levin or Levine. It's a Southern California company that makes these really nice, very expensive watchmaking machine tools. And those are the components that they're using for some of their in-house built machines or for some of their specialty work. So there's a huge amount of crossover.
definitely. Well, you mentioned your internship. You mentioned some laboratories. Let's get into what you just experienced.
Yeah, that again was just one of the coolest things that's ever happened to me. It's definitely up there, like top 5 best life experiences. I cannot say enough good things about that shop, that organization, the people that I worked with. It started out as a tour. So, basically through Instagram, it turns out like a lot of the supervisors at the various different shops at Livermore Lab are fans of the Instagram account. For whatever reason, they think I know what I'm talking about. Don't tell them. Um, so they contacted me and said, "Hey, has anyone reached out to you about doing a tour?" So I said no, and they set up this really awesome tour for our students. And I took like 20 students with me. Um, it was fascinating. They, trucked us around in shuttles. They took us to 3 different shops. The main Bay facility, their main machine shop, which is where they do most of their like general purpose machining. There's also another building which is like mostly a manual shop. It has some Akumas in it, and that's sort of the apprentice building. So like I think actually everybody who starts first goes there, not just apprentices, but apprentices spend a few years there developing their basic skills. And then the other shop that they took us to was Target Fabrication. So Target Fabrication is works directly for NIF, which is the National Ignition Facility. And this is the world's largest laser based inertial confinement fusion research device, ICF. So I'll explain what that means in a moment. It's the world's most powerful laser, okay? And if you've ever seen Star Trek Into Darkness, like one of the new Star Trek movies, there are several scenes that are actually shot next to the main chamber at NIF. So it's this big sphere that has a whole bunch of like rectangular tubes going into it. And so, like, yeah, the engineering section or the warp core in that movie, that's actually NIF. They were actually allowed to film in there, which I don't know
Really?
how they, yeah, I don't know how they managed to do it, but it's super cool. You can see Simon Pegg standing next to Super Science. It's very cool. Um, so what they're trying to do at NIF, and this was, I think it was in the 1990s that they built this thing. It's like a natural evolution for bigger and bigger and bigger lasers, because they realized very early on that lasers could be used for fusion ignition, although it turned out to be way more difficult and complicated than they thought it was, because there's some stuff that happens, during a shot, which is, yeah, just more complicated than they expected. But in any case, so it's basically starts off as like a pen laser. It's not more powerful than that. And then they optically pump this laser beam back and forth and back and forth in this um, enormous, like, I don't know, I think it's something like, I can't remember how long it is now. It's a very long sort of warehouse that has these big tubes going through it, and the laser light is going through the tubes. And by pumping it, they increase its energy, and then they split it off into 192 different laser beams that all come into this sphere at different angles. And all of that light is pointing at what's called a Hohlraum, which is this little hourglass looking thing. And inside of that thing is a pellet of deuterium, heavy hydrogen. It's got a proton and a neutron, so it's heavy hydrogen. And they're actually not really pointing at the pellet itself. What they're doing is the lasers are shooting X-ray into the Hohlraum, and it resonates inside of the Hohlraum, and the pressure from that is what causes the pellet of deuterium to have ignition. So it causes a nuclear fusion reaction.
Hmm.
So that's very, very, very cool. They use it for a whole lot of different things. They, of course, the way that they sold it is like, hey, this is going to be fusion energy, which is a wonderful dream. It's, like I said, way more complicated than anybody initially thought it was going to be. And so they're not there yet. In fact, they're not really that close. I think in 2021, they had a test shot that reached like 70% of the energy that was put into it. So 70% energy output that was input, which is a big deal, but obviously they're pretty far off. And it's like they can only shoot, they have like one shot per month or something. But in order to turn this into a power plant, I think they would have to have like multiple shots per second.
Oh, wow.
So they're pretty far off. But they're doing really, really cool work there. Basic scientific research. There they can recreate the conditions within stars. They can recreate high pressure but low temperature conditions as well. So like, what's going on in the center of a planet, for example. And of course, they also use it for what they call stockpile stewardship, right? So again, I can't remember exactly when this happened. I think it was the 1990s, but they decided to stop testing nukes by blowing them up. So instead, they use simulations. So that's part of the reason why Livermore developed their supercomputer program, was to do simulations, and then doing experimentation in, these laboratory environments like NIF. Okay, so that's the other reason. And for those two things, I mean, it's an amazing test apparatus.
That's really cool. Kind of a tangent. Do you watch Smarter Every Day on YouTube?
I've watched a few episodes.
So you were talking about nuclear testing, and he's got a series recently where he goes to Kodak in New York and sees how their film is processed. But I think it was one of the first episodes in that series. I want to say it was him, but maybe it was somebody else on YouTube. But they were talking about how Kodak knew before the public when we started testing nukes in the U.S. Like before anybody knew, because they were generating all this film, and all of their film factories are based on rivers because they need water as part of the process. and they were having film come back that had all these pinholes in it, and
Oh,
they
wow.
traced it back to radiation fallout from the nuclear tests that was falling into rivers and then making its way into their factories and actually depositing on film that supposedly had never seen light, had never seen any of the stuff, and was creating pinholes on. I can't remember if it was X-ray film or if it was just normal film, but I think were making enough of a fuss about it or talking to enough people that the government had to reach out and say, "Hey, this is what's happening. We'll let you know before we do a nuclear test so you can stop producing film on the following X number of weeks or days or whatever, so that it doesn't ruin your film. You can't say anything to anybody."
Wow.
Yeah, I thought it was so
That's
interesting.
that's amazing. I've been wanting to watch that particular series on Smarter Every Day because on Textbook Tuesday, I posted a book called Making Kodak Film, which is a really cool book. But then shortly after that, it was like 2 days after that, this series came out.
Oh,
And
cool.
so I haven't even had a chance to really watch it, but I'm really excited about it. Now I'm even more excited. That's awesome.
It's so well done. He really does a great job with those videos. But yeah, it's enough over my head that I've had to rewatch some of them, or like I'll pause and then kind of think on it and then have to go back, because it's not like one of those things that I inherently understand. There's so much chemistry in addition to physical, you know, development of all these processes that it's just a lot to take in, but it's really cool.
For sure. So what Target Fabrication does, just to go back to that,
Yes.
is they're not making the whole round, because the whole round is like, that is commercially produced by, another company in mass quantities, right? They already figured those out. There's really no R&D that goes into those, right? So the lab doesn't do production, right? They do R&D. So they're not making the whole rounds. What they're making is the targets. That's why they call it target fabrication. And these targets are like the test specimens. So they're very, very small little artifacts which they put on the side of the whole round. And as the nuclear fusion reaction occurs, they watch what happens to the target. These parts are very, very, very small, because even though this is the world's largest laser, it still has a limited energy, right? So you got to make everything on like a tiny scale in order to get really good data. And it's not just small in terms of, its size. They also like to use materials that are very low in density, right? So they're also using like foams and aerogels and stuff like that. And the thing about these targets is that typically the targets are they're like the calibration artifacts for the experiment. So they typically have a very specific, usually relatively simple, but a very specific geometry that's built into, they're like little rectangular plates, like, maybe like 1 or 2 millimeter square or something like that. And they have this very specific geometry in them. And the geometry needs to be well known, and it needs to be extremely high accuracy. Because if they know what the geometry of the target is, they can feed that into the computer, right? And they can they can compare the test results to their computer simulation to figure out if the computer simulation is accurate, basically, is what they're doing. So for like stockpile stewardship, for example, the computer simulations are tested via experiment to make sure that they're on the right track. That's essentially how it works. So when I'm saying that these targets need to be very accurate in their geometry, I mean that the tolerances are typically within 1 micron. Many of the features and structures can be no bigger than like 100 nanometers, which
Jeez.
is which is a zero point 0.1 microns, and the smoothness, or like the surface roughness, is on the order of 1 nanometer.
And this is all on foam or low density materials.
Well, so typically I have to be very careful about what I say, because this is, a government institution that does classified work. So uh, I can't really talk about the specifics of the parts that they make, but I can say that in general, they are typically interested in like pure elemental materials, because part of what they're doing is like building up a database of how these various materials perform or behave under these conditions. And yes, aerogels and foams because of their low density characteristics.
It sounds tough, but also like it must have been a very interesting internship then.
It was super cool. It was super cool. And to demonstrate like how big of a deal accuracy is in these experiments, there's one particular experiment that they do where it's a very simple little part. It's like basically it has like four little steps in it. These steps have, well, I don't know, I can't remember the numbers exactly, but the very small piece has these very small steps in it, and the surfaces need to have a flatness of 50 nanometers or less. So just for people listening, 1 microinch, 1 millionth of an inch is 25 nanometers. So this is 2 millionths of an inch flatness. It's not a big part, but that's still pretty gosh diddly darn flat. And before they were able to achieve like 100 nanometers in flatness, so twice that, still only 4 millionths of an inch in flatness, pretty gosh darn flat. But because it was only 100 nanometers flatness, in order to get really reliable data, they had to do 4 shots, which is expensive. And because of improvements in the machining technology, specifically improvements in diamond turning technology, they were able to get it down to 50 nanometer flatness or less. And so now they get the same quality data in only 1 shot. So this is a practical example of what tolerances really matter. And it's not a matter of, well, it just needs to be good enough. It only needs to be 10 times better than the, like the typical example for tooling, for example, like you're working in tool and die, the tool needs to be 10 times more accurate than the thing it's making as a general rule of thumb. It's not like that, right? It's as close as you can possibly get it because you're going to save time, you're going to get better data.
That's crazy.
Yeah.
Wow. Well, so one of our questions from Silos Garage was tell us about the stuff you did with diamond turning and then the most valuable piece of information you learned while there.
So this whole shop is, and they just recently moved like a year ago. This whole shop is decked out with Kern milling machines. They've got 4 of them. So they have 2 Kern Evos and 2 Micros. So Kern milling machines and more nanotech diamond turning machines. And they have, I can't even remember how many more nanotechs they have. They had just basically standardized on this machine. It's a Moore 250 UPL, a super cool machine. Diamond turning, it's sort of unfortunately named because it makes it sound like it's just a lathe and you're using a diamond to cut things. And that is what you're doing, but I wish they would have called it like ultra precision machining or something like that, because you're in ultra precision machining, you are typically using diamond as the cutting tool because diamond is hard, because diamond wicks away heat very, very quickly. Diamond, you can sharpen to atomic sharpness. And one of the big tricks in being able to make really high accuracy, smooth surfaces is the ability to cut the material with minimal surface damage. And that requires a ridiculously mind-blowingly sharp tool. And that's what diamond offers. So that's part of it, right? But the other part is the machine. So you can use diamond on any machine and you're going to get like a pretty decent finish. But to get that super high quality finish and high form accuracy, you need a special machine. And these are machines which have air-bearing spindles, which have hydrostatic weigh systems, which are using sophisticated high-resolution feedback sensors. They're using linear motors for their drive systems. They are, in general, these diamond turning machines, basically lathes, but they're sitting on top of just a big granite slab. The granite slab itself is sitting on pneumatic isolators, right? So that they limit vibration from the environment. And then that, of course, is like on a relatively heavy duty, like fabricated steel base. And so lots of different things are getting actively temperature controlled. So yeah, in many cases, the air that is running the air bearing spindle is temperature controlled. The oil in the hydrostatic guideways is temperature controlled. The environment is typically temperature controlled, so it's 68 degrees or 20 degrees Celsius, um, within like a half a degree plus or minus. And then in many cases, the machine itself is being temperature controlled inside of the enclosure.
Wow.
Not on all machines, right? But these are the kinds of this is where we're going.
Right.
And the other thing too that was very interesting to me is that these are not exactly like lathes that you're familiar with. A typical lathe has the headstock with the spindle in it that is static, and then you've got the z-axis which rides on the bedways, and then on top of that you've got stacked the x-axis, right, which goes, which runs transverse to the spindle. One thing about that is like this is very, very useful when you're doing turning operations, right? But when you stack the axes on top of each other like that, the errors in the axes compound, right? So now if you've got a z-axis error, you also have an x-axis error. So for these diamond turning machines, they decouple those two axes. So now you've got one of the axes which moves the spindle itself. And so on modern diamond turning machines, this is typically the x-axis is the spindle, and then the z-axis is the tool. So they
Really?
decouple those. Yeah. It's really kind of weird looking when you first look at it, but it's very, very effective. So this is, they're thinking in a different way about machine tool design. And the cool thing is that the history of diamond turning machining developed in the United States. I think it first got started in the 1940s. There were some commercial entities that were developing that technology. It's basically all like military stuff at the very beginning because the tolerances required for weaponry were really exacting. And so in the 1940s, it sort of started, but it really hit its stride in the 1960s at the Oak Ridge Y12 plant, another national laboratory that was developed during the Manhattan Project in the 1940s. At this facility, they started developing an air bearing spindle that was really very robust. I think it could handle like 400 pounds or something on its like you could hold apart 400 pounds in weight, which is really significant for an air bearing spindle. So this huge, they're like counterposed hemispheres. And there's actually a really cool article that I can share. I mentioned it in a video that I did on air bearings, Introduction to Air Bearings on the Machine Tech video blog. I mentioned this article that was written about how they made that air bearing spindle. And I believe that Harold Arneson of Professional Instruments Company fame, who started that company, worked on this air bearing spindle at Oak Ridge. And one of the things that national laboratories do is that they will develop technologies and then it's part of their mission to commercialize them. So in the process of commercializing this technology, PI was started. And so all of this sort of like interrelates, right?
Yeah.
So Professional Instruments Company, for those of you who aren't familiar, like go back and watch the episode with Cyrus Lloyd. He just did an internship there. It was an awesome episode. It's a really cool company. They are the world's preeminent air bearing manufacturer, both spindles and translation stages and stuff like that. Super, super cool. So that technology that developed in the 1960s ended up getting further developed by other national laboratories, and especially Livermore Lab. So diamond turning was really perfected as an art at Livermore Lab. So that's why it's so cool to be doing diamond turning at Livermore Lab, right? Because there's an enormous amount of institutional knowledge about those machines. So in the 60s and 70s, they developed DTM 1, 2, and 3. So this is diamond turning machine 1, 2, and 3. And these were absolutely superlative machines that were developed, again, for like weapons work. It wasn't until like the 80s and 90s that diamond turn machining was really commercialized for other uses. But primarily what they're trying to do is make optics, right? That's really the development or like the motivation behind diamond turning. Because and actually, Cyrus mentioned this on his episode when he was talking about different ways to make super, super accurate forms. So for optics, you need typically an aspherical form for something that's going to be a really high quality optic that has low aberrations. You need an aspherical form, and it's got to be super, super, super smooth because it has to be reflective. And to make that, traditionally, what you would use is grinding, then lapping, then polishing, which are these sort of indeterministic processes where you've got a lap and then some loose abrasive, and you're rubbing it against the part. And it's a sort of guess and check process, right? I mean, people get really, really good at it, but it requires an absolutely incredible amount of skill. And ultimately, it's still a guess and check process. The great thing about diamond turning is that it's a deterministic process, right? You have your two axes, you have your work spindle, you have your cutting tool, and you can specify the geometry that you're cutting, right? And so it's very easy to control the various factors involved, various parameters, and you can create super high accuracy forms, basically any form that you want. And it's almost good enough for all applications right off the machine. I would say that in general, diamond turning is used predominantly for like infrared optics because like infrared, literally like less than red on the light spectrum. This is longer wavelength, lower energy light. And so typically when you're working with optics and lower energy light, the tolerances for the optical components are lower. So you think of like when you get all the way down to like radio waves and you think about radio telescopes like Arecibo, which is like exploded, so it's not with us anymore. But the Arecibo Observatory is this huge like concrete dish or whatever. And that form is not particularly precise,
Right.
right? But then when you get into like X-ray optics, now it has to be ridiculously precise. So you're not making X-ray optics with diamond turn machining, or at least not without post-processing through a more like
Right.
traditional method. But in any case, so this is what you're doing. And so the diamond turn machines were really cool. I think a lot of them had like oil bath. So you had temperature controlled oil that was dumping on the machine itself. So like the operators were wearing raincoats and galoshes operating this thing. But that's how they were maintaining the temperature because it's much easier to maintain the temperature of the oil or the coolant than it is to maintain the temperature of the air. This then led to, it was in the 1980s, to the large optics diamond turning machine, LODEM, which, if you look it up, it basically was, for the longest time, the world's most accurate lathe. And this was an enormous structure. It was sort of, the one interesting thing about it is how they did the temperature control, because it was in this sort of like matryoshka doll or like Russian nesting doll kind of design where they had a room with the machine that was temperature controlled, that was inside of another room that was temperature controlled, that was inside of another room that was temperature controlled, etc. And so all of these sort of support operations were done around the machine, but the machine was in the center, right? So by the time you got to the inside structure, it was really, really, really stable. So I don't think that one did have oil bath. The actual structure of the machine was, I think it was just like fabricated steel structure, but the metrology frame, which was different than the structural frame, right? The metrology frame was made out of super invar. So this is a really smart way to design this machine to get the best accuracy, because the metrology frame itself was providing a constant feedback, and it was all laser interferometers, by the way. So this is ridiculously high resolution. It was constantly feeding back information to the motors, to the control. And so they were making updates, right, to the position of the machine sort of on the fly. So there are a number of different ways when you're designing a precision machine that you can take the errors out of the equation. And one is that you can just make a really, really accurate machine, right? But of course, that's expensive and materials move around and they wear. So that's maybe not the best option. But another way that you can do it is to have sort of active feedback, right? So the machine maybe isn't as precise as you want it to be, but your metrology frame, your metrology system makes live updates to control the position, right? And so that's what was developed on Lodum. And there are some really cool articles that were written about this. Actually, in Alex Slocum's Precision Machine Design, there's a whole section on Lodum. There's a guy, Leighton Hale, I think is his name, was an engineer, precision engineer at Livermore Lab, and his PhD thesis included a lot of information about Lodum. So there are places where you can go to learn more about this. Lodum is no longer used, by the way. It was superseded by other commercial machines, and I don't know, they mothballed it, and then I think they tore it down. Somebody said it may have gone to another university. I don't know. I sort of questioned that because it's just such a purpose-built machine. It was built to make optics for like space telescopes and for like the Star Wars program. And
Right.
space telescopes of that type are like not really in vogue anymore. So, its whole purpose is kind of not non-existent anymore. Although I think they did make some secondary mirrors for the Keck telescope in Hawaii, which is pretty cool.
Yeah, I was born in Hawaii, and we actually went to the Keck, and it was one of the cooler field trips I did as a kid.
Fascinating place I've never been,
Yeah.
but would love to go. See
Another
that
one you've got to come to is if you're ever in Tucson. I think they're still doing tours, but under our stadium here for the University of Arizona, they have the place that they cast and the place that they polish the giant mirrors from the mirror lab here, and we've made them for all the big telescopes in Chile and all over the world. But it's this giant spinning oven basically that melts all the glass and creates these giant forms, and then they take them and transfer them over to this giant area that they have a robotic polisher that goes around and forms the mirrors.
Wow. Yeah, so like I've been on the website for optics at ASU. But of course I've never been there. I would do they let people do tours?
I did one maybe 5 or 6 years ago. I assume that they're still doing it. It's like
Sick.
fascinating. Like you go
I
and
would
you're like,
love
oh,
that.
here's this giant stadium, and then you'd like kind of take a little staircase down, and it's like, oh, there's this giant spinning, you know, oven basically, and then they like to walk you over to this other area, and they're like, oh, there's all these people with booties standing on a mirror as this like robot spins and polishes them and kind of goes around, and like they have a
Oh
way of
man.
testing it and like reflecting light into it and have a sensor hanging from the ceiling that they can actively analyze the state of the mirror, and it's
That's
super
so
cool.
cool.
Yeah,
That is awesome.
it's well worth, if you're a big optics nerd, which it sounds like you are, it's well worth coming out and getting a tour for sure.
Yeah, I will do that for sure.
So to get back to Cyrus's question, what's the most valuable piece of information you learned while you were at your internship? And actually, to piggyback on that, what is something you've learned while you were there that you're going to carry into your day-to-day machining?
Oh, that's such a good question. There were so many things that I learned there. I'm still processing all of it. And, the ultimate use of all of this is going to be the development of curriculum for students. Um, I don't want to count my chickens before they're hatched, but I'll just say that we may be getting some equipment donations that will up our game even more in this realm. So, in the process of thinking about developing curriculum for this, I reached out to a number of diamond turn shops and asked them several questions, including like, what are you looking for in diamond turning technicians? And what people said was actually pretty consistent. So 3 rules for diamond turning. Here they are. 1, don't touch the diamond turned surface. It's never going to be as good as it is right off the machine. There is nothing you can do to it to make it better, so don't touch it.
I laugh because I know that I would for sure by accident touch a diamond turnstile. Be like, ooh, pretty, and touch it and be like, oh, just ruin that. Great.
It's so pretty. It's so pretty. I mean, the surfaces coming off the machine are mirrors. They're gorgeous. I mean, it's so weird to be in this shop where everything is reflective. Like everything in the whole shop is reflective. You can see your tool, like the way that they set tools off. They know that their tool is getting close to the part. If they're gonna you do like a dynamic touch off or whatever, it's like they're looking for the reflection.
Oh, that's cool.
And you just judge based on the reflection. When the two reflections touch, you know that you're there. So so number two, everything is rubber. Of course, Robin Renzetti says this all the time. It is so true. When you are looking at, material or parts that are really small, you're looking at really small tolerances. Just everything's moving around all the time, right? And actually metals are not particularly stiff, right? So everything is rubber. The third thing is that everything is a thermometer, right? So, and I forget exactly what it is for steel, but it's, these materials move around a lot more than people give them credit for. It takes absolutely nothing for a part to grow a tenth of a thousandth of an inch or whatever it is. It takes nothing for that to happen. So if you're taking really careful measurements and you're concerned with things like absolute size, you can't be touching things. You can't be breathing on them, right? The environment has to be temperature controlled, or at least where you're measuring has to be temperature controlled. So one of my favorite things to show students, actually, and this works really well on a cold day in the winter, put a really accurate indicator on top of a gauge block. And then cup your hands around the gauge block. Don't touch anything, just cup your hands around it. And the heat coming off of your hands will start causing the gauge block to rise. And you can see it happening in real time, and that just blows people's minds. In general machine shop work, maybe you don't notice things like that, but as soon as you start working in tenths, it's noticeable. And if you're working in microns and nanometers, it's really noticeable. So those are the three rules.
Okay. Well, one of his other questions was, what's the most surprising and unexpected thing you learned there? And so that might be, along those lines, or what else did you learn there that you were like, I never would have thought about that?
Okay. Three things. One, cleanliness is key. So I guess I'm adding to the rules of diamond turning here as we go. Cleanliness is key. So at Target Fab, all the work holding is done with adhesives and vacuum. Right? They're not using magnets, they're not using clamps. I mean, all of those things distort parts. And so for really, really, really high accuracy forms, you need extremely low distortion work holding. So vacuum is a great way. And typically what they're doing is they'll have, like a pocket in one flat surface, and they'll put another flat surface on top of it. And it's just two super flat surfaces sealing against each other. No gaskets or O-rings or anything like that, just two super flat surfaces. So to make those super flat surfaces, they either have to lap them or they have to diamond turn them. So basically all the fixturing gets diamond turned so that you can pull vacuum on them. But then adhesives is the other thing. So, basically, they have this whole elaborate system, this in-house designed modular work holding system that is, it's really interesting. I'm actually going to post about it a little bit later because they gave me a PDF of it. So I'll talk more about that later. But essentially it's like the little vacuum chucks locate on a carbide ball, and then there's a flat surface. And the flat surface is what gives it sort of angular rigidity and also is the sealing surface. And they use this not only for work holding in the machines so that they can take the part around between machines from the mill to the lathe or whatever and like get less than 1 micron repeatability, but also they use it in what they call a manipulator. And the manipulator is gosh, you can do all kinds of things with it. They use it for initial glue ups when they glue the parts to the vacuum chuck. And so the manipulator is there to facilitate that. But you can also do other things like parting off on it. I mean, there's like really cool things that they do. But the point of all this is that those two flat surfaces that are both for sealing and for location are obviously really important. They need to be very, very flat, which means that you need to keep them clean because if you've got anything in between them, it's not going to hold vacuum. And when you try to suck vacuum on it, it's going to crush the surfaces. And now you'll be sitting on like a divot or whatever.
Right.
So, what they do to clean these surfaces off as they're assembling them is amazing. Believe it or not, they actually use eyelashes. They take human eyelashes and glue them onto a stick. And then they're looking at the interface between the two surfaces with a stereo microscope. So everything is done. I mean, the parts are so small, they're like 1 millimeter, 2 millimeters in size. Everything is done under a microscope. So zoom video cameras, so they can watch it with the enclosure doors closed, or stereo microscopes when they're doing initial setups. And they'll find individual flecks of debris and flick them out with this little eyelash attached to the end of a stick.
What? It sounds like a joke. Like it doesn't sound real. That's crazy.
It's ridiculous, but it's so effective. They also have a little like static charging gun. And so they charge the eyelash so that it'll actually attract debris off of the surface. I mean, I used it a whole lot, dude. It sounds ridiculous, but it works so well. And so before anybody thinks, no, there's no apprentice whose job it is to like pluck out his or her eyelashes for science. They typically go with these like fake eyelashes, but the real human eyelashes are preferred. They have some kind of texture to them that works best. And so these folks are walking around to all of the microscopes in the shop, and there are many, many of them, and they're always checking them to see if somebody's eyelash has fallen on one of the eyepieces because they're so highly coveted.
That is insane.
It's so funny.
Wow.
Yeah. So that was one of the most surprising or unexpected things that I found out there.
Definitely qualifies.
Yes. Two things that are really, really valuable. So one is something called off-axis turning. And so, you're working on a lathe, you're setting your tool height, right? And you're setting it so that the tip of the tool is on center of the spindle axis. So that as you're facing to the center of the machine, you don't leave a little nub, right? Because if you're too high, you're going to have a rounded nub. And if you're too low, you're going to have basically like a little cylinder of material that wasn't cut in the center of the part. In a typical machining operation, it's like a nuisance, right? But when it comes to diamond turning, that little nub, even if it's only a micron in size, will spoil the whole geometry of the part. So setting tool height is extremely important, right? So the actual tool holders themselves are on little flexures. They've got this whole process that they use for setting the tool height. Like, for example, they intentionally set it slightly low and then take a cut across the face of something and then remove the part and take it over to a measuring microscope or some other optical measuring system. And they measure the size of the nub. And if it's 4 thousandths, they move their tool up 4 thousandths.
Oh, wow.
And so that's how they're getting rid of this stuff. It's, again, like at this level, everything is sort of, trial and error. You're testing and checking every single thing in process. So that's how you would get rid of a nub. But one of the best things that you can do is just to eliminate the issue of nub generation. And that is turning off axis. So imagine you've got a faceplate and you've got a part that you want to make flat, and you mount it some radial distance from the center. And of course, for balance purposes, you have to mount another thing of the same weight on the other side of this faceplate. And actually, the cool thing about these diamond turning machines is that they have built-in dynamic balancers. So anytime you change your setup, you are running the dynamic balancing routine, because even tiny little errors are going to show up, right? So by turning off axis, you no longer have this issue where the accuracy of the surface is dependent on the tool center height. You can be significantly off, and you'll still get a really nice flat surface or whatever the geometry is. So
Interesting.
off-axis turning is really, really slick. And that's not something I really thought about, but for the ultimate flatness on a lathe, off-axis turning is the way to go.
I like that. His last question was, can he come take a sabbatical at Laney College and have a precision machine tool building play date extravaganza?
Yeah, literally any time.
I thought that you would be happy to do that. Obsidian Tools asked, in what shop facility would you like to get a tour and why?
I think the standard answer would be Professional Instruments. I would love to go check out what they're doing and see how they're making all those spindles. I wonder how much of that information they'd be willing to share with me, but I feel like that would be very instructive. I'd also like to check out some more like diamond turn shops. There's one called 26 Incorporated, which is a very, very large shop. I'm actually supposed to be talking to their machine shop manager later on, but they use lots of diamond turn machines to manufacture like IR optics and CO2 laser optics, and they're out in like Pennsylvania. So I would love to see how they're doing their fixturing and how they're doing their programming and how they're doing their measuring. A lot of the measuring is done with like white light interferometers, which create these three-dimensional scans of parts. So diamond turning machines often sort of go hand in hand with white light interferometers, and I would love to see that as well.
Okay. We had a couple of general questions about teaching. So Mudslave Burner and NYDLS 30 both asked how to be a good teacher, how to be better at teaching manufacturing and technical concepts. What advice can you give people on how to reach people in such a technical subject?
I mean, it's an ongoing experiment. I don't think that I have like a magic bullet here, and I make a lot of mistakes and sometimes don't reach people or sometimes have to try multiple times to really get a point across. A little bit of enthusiasm goes a long way, I'll say, for bridging that gap. I think one of the most important things that you can do is to practice explaining technical concepts in simple, straightforward ways. I think this is very important for people to grasp concepts, because ultimately you want to teach more than just skills. You want to teach concepts. And so explaining these things in simple, straightforward ways is very important. And one of the best exercises actually is trying to explain something technical to someone that has like no background in the field. I mean, not a child, like an adult, right? But I don't know, a colleague or a spouse. I know I really abused my wife's time, especially when I first started as a teacher, because I ran so many things by her. And like I often joke that she could get a job at a machine shop just based off of the interview, because she has absorbed so much just through osmosis or those kinds of experiences. But if those people can grasp the gist of what you're saying, then it's probably a good explanation. So it's a good exercise.
Okay.
Um, the other thing, and I think I said this in the first episode, was that telling someone is worse than showing them, which is worse than having them do it. So priority should always be having somebody do something, even if that's like you're talking them through it instead of like, hey, I'll do one, then you do one. I mean, that's good, but it's even better if you have them do it and you talk them through it. It means you have to be very patient. You have to let people try things for themselves. You have to be okay with people making mistakes. But I think that's the most effective way to learn. And it's also, it's very high reward for the person who is doing the learning, because they're the ones who did it. And there's a high likelihood of success because you're there to help them do it. So once people get a few wins under their belt, they typically are more interested in the subject. It means that, you have to do a lot of choreography, because you're trying to push people to go outside of their comfort zone and try new things, but you really need to do that within like defined limits and offer lots of support so that it is really achievable by the person. Like we always try to tell people, you can do it, but you have to make sure that they really can do it.
Right. So would you say that that's the major hurdle in teaching new machinists? Craig Camp asked, what do you think the major hurdles are when teaching new machinists, and what are some ways that you've overcome these hurdles? Would you think that it's just getting them to realize they can do it, or what would you think is the major hurdle in teaching somebody machining?
There are a lot of different ways I could take that question. I Well, the initial hurdle is just like interest, and I'm not really sure that you can generate interest. Right? It has to come from inside of a person for whatever reason. It's like they're looking for a better job. They are really interested in the technical side of things or whatever it is. There has to be some interest there. In terms of actually getting people to the point where they are now machinists, right? They have interest, but like getting them to be machinists, you can teach skills all day long. You can teach concepts, but there's like personality traits or like attitudes that are really hard to teach, although they can be learned. Like patience is something that machinists need to have. And like, I'm not a patient person at all. And I've had to learn patience through machining because basically I hated by trying to rush things, I ended up creating rework, and rework is where all the time is lost. And so, smooth is fast. But there are other things like confidence issues, both lack of confidence and overconfidence. And like lack of confidence for students who are seeing this stuff for the first time, it's very intimidating. There's so much information that you need to have in order to just do simple things in a machine shop. So the initial like slope of the learning curve is very, very steep. And sometimes people just need you to tell them that it's okay to do something. Like, it's okay to stick that tool blank into the grinding wheel with your pale, fleshy little fingers right next to the spinning abrasive wheel. Like, that's okay to do as long as you remember the things that we told you. Or it's okay to take that big cut. Like on the project where we use carbide tooling on the lathe for the first time, there is a 260 thousandths step, and this is in a steel part. And we don't just suggest, we require students to rough that all down in one pass. 260 thou is not a super huge cut to a seasoned machinist. But if you're someone who has never turned with carbide before, like your whole life is flashing before your eyes when you think about a cut that deep. And so you got to be there to say, you can do it. It's okay. Take the cut. And it's hilarious to watch people, they kind of pump themselves up, like, then they engage the feed lever. And then as soon as the tool touches the part, they jump back. Big chips are peeling off. And then when they realize that there's no danger, no imminent danger, they slowly come back in to check out what's going on. But that is a really important moment for basically every person I've seen come through the shop. So for lack of confidence, you need to be there to tell them it's okay. You can do this because we've choreographed this environment so that it is possible and you're not going to get hurt.
Okay.
But
I
then,
think that's I think that that's missing with a lot of people. Like I know I've definitely, even just teaching simple concepts to people, have not done that well of a job maybe enabling success. I've very much been like very hands off in the past. So that's a good thing to know.
I think so. Then the other issue is like overconfidence. And I think overconfidence comes from, people having a little bit of experience, enough experience to become complacent. And I would say this is the most dangerous point in someone's career in terms of like their own personal safety, because they forget that the machines can do unpredictable things or that they're really very, very powerful. And so making sure that people stick to the safety script is really important at this point. But it other than the safety stuff, you really need to let people work through this overconfidence period themselves. They're going to make a lot of mistakes. They're going to scrap a lot of parts. because they haven't really formed the feedback process yet. They think that everything is predictable, and then they're confused and sometimes even angry when things aren't predictable. But they will eventually learn. You just have to let them learn those lessons the hard way. So I think lack of confidence, overconfidence, those are two things. The other thing is developing critical thinking skills. I thought for the longest time that it was just natural that everybody was able to perform a task, a specific task, and then extrapolate generalities from that task and then reapply them to another specific task that is different but similar. I thought that everybody could do that. But it turns out that that's actually a learned behavior.
Hmm.
So you have to teach people how to do that, or you have to encourage them to learn that on their own. And, when we're talking about this, I've used the word choreography a lot. You're choreographing this activity in this very clinical environment so that students can succeed. As part of that, you're providing instructions, for example. One of the issues with instructions is that, and I think this happens to everybody. I mean, it even happens to me that when you have really detailed instructions, your brain turns off. And it actually just happened to me. I was making this mechanical wall clock, this wooden wall clock, and I was following the instructions. And there was an error in the instructions. Two components were reversed in the drawing. And so I installed them that way, even though I had just learned the way that they were supposed to be. But I was just reading the instructions and following the instructions, and I turned my brain off.
Right.
And I think this happens to people, right? If you have instructions that are too detailed, and especially when people don't really understand the motivation behind why you're doing it in that particular way, then they won't really learn to think for themselves. So it's that balance of having the right guidance, enough guidance, and also letting people make mistakes for themselves so that the lessons become very intuitive, right? That's really tricky to do. In the program, like I said, we teach more than just skills. We teach more than just how to make this one part. We teach concepts. We explain them thoroughly. We do lots of demonstrations so that hopefully this becomes intuitive for people. But also throughout the course of the various different courses, we take people's training wheels off more and more and more. So at the beginning, you're following instructions. You've got demonstration videos. By the end, we give you a blueprint and some material, and you develop your own plan of operations. You figure out how to do the metrology. I mean, you can talk to us, of course, like the conversation is very important, but you're pretty much doing everything on your own. So over the course of basically three classes, by that point you're doing most of the things on your own with discussion from your instructor. So that's kind of what you have to do. You sort of you progressively take the training wheels off, I suppose.
Okay. So when you're, because I definitely have struggled from that same viewpoint where I expected people to intuitively pick up on things the way I do. And I don't know if it's because of how I grew up or, the way I was taught as a kid. How have you changed your mindset? Because I know for me, it can be very frustrating when I think that something is so obvious for someone. I'm like, oh, well, you just learned this. Of course, it's the same thing. Like, why wouldn't you just do it again? How have you changed your mindset and how have you communicated to those people and kind of learn that behavior or help them learn that behavior? Because that is, I think for a lot of us in the community, you get in a trainee or you deal with a colleague or something like that, and you're like, how can you be so dense? And you don't realize that like that is a learned behavior. I have only in recent years really kind of realized that.
You and I have a background in like formal academic education, right? Like we
Right.
both went to college. That is not true for a great many people who are in the trade. So when I first started teaching, I started teaching like I had learned at the university. So very lecture heavy. And it's like, I tell you something, you take notes, you retain it, at least for the test. And then we say goodbye and we never see each other again. And if you fail, that's on you, buddy. But that's not how trades education works, right? In trades education, most of the people who are in the trades are kinesthetic learners. They have to touch something, they have to interact with it in order to understand it. It's not enough to tell them something. In fact, in most cases, it does nothing to tell them something, unless they have this sort of like background experience in academic environments. And you don't even realize that, like, learning how to learn in that environment is a totally learned behavior, right? So if you don't have a background in it, it won't make any sense to you. You won't do those simple things that you and I take for granted. So getting people, like, even when you're like you're talking about something, take out a physical example of that thing and then hand it to the person. Even if all they're doing is touching the thing, rotating it in their hands and looking at it, that could be the thing that helps them to bridge that gap. And the best thing, of course, is to have them do it. So after you've talked about it, maybe after you've demonstrated it, have them do it and talk them through it, and then have them do it without any help, right? People really need to do it in order to understand. And that is why we have a project-based curriculum. That is why we are so big on hands-on learning. All throughout COVID, right? We were in the shop teaching people hands-on learning because it is the only way to teach these kinds of skills, and especially because the types of people who go into the trade are the types of people who are kinesthetic learners and they don't have a background in academic education.
Okay, I think that's a great answer. Let's see some quicker questions. Tux Garage says favorite machine to run and favorite ice cream flavor.
Favorite machine to run, I would have said before that it was the King vertical turret lathe that had a big 6-foot swing that I ran at my first shop. That was a really cool machine, but it's been superseded by the Kern Evo. I ran that Kern Evo exclusively during my 2-week internship, and I specifically requested it because it's very similar to the MMP that we had donated to us by Kern. Um, it's it's just such a joy to operate that machine. It's just the right size. It's relatively small. The ergonomics are great. There's a huge window on the sliding door. The console articulates, and you're like right there in the action. The Heidenhain control is surprisingly fun and intuitive to use. And I don't know, it just, like, by the end of those 2 weeks, not very long, it just felt like the machine was an extension of my body. I really enjoyed running it. It's great that it holds, like, once you dial in the tools, this thing is holding, plus or minus 1 micron all day long without even thinking about it. So it's just really rewarding in that way. I'm so used to, like, having to cowboy the machine to get it to do what I want. And then here's a machine that just does it when I ask it to. And that reliability means a lot to me.
Okay. And then favorite ice cream flavor?
Tillamook, Oregon hazelnut, and salted caramel. It's not just my favorite ice cream flavor, it is the best ice cream flavor that has ever been and ever will be. And that's not an opinion, that's a statement of fact. So go have it right now, and you will not be disappointed.
Okay. NYDLS asks, how did you become pals with Tom Lipton?
He was my boss at Lawrence National Laboratory.
He asked, do you have the number for Dan Gelbart?
No, I'm fairly certain that Dan Gelbart does not know I exist.
All right. And then last question from Oakland Jesse. What would your second dream job be?
It would be working at Target Fabrication at Lawrence Livermore National Laboratory. And by the way, they are hiring, folks. This is really, cannot say enough good things about this place. So Livermore Lab was voted like number 6 out of 100 best places to work on Glassdoor. So the organization itself is just great company to work for. And this, the machine shops in particular, Target Fabrication in very particular, it's just got a great group of people, a really well-equipped shop. Like, they are not messing around with their equipment. Like, they're not, like sometimes they say tongue in cheek, we're not here to make money, we're here to spend money. They don't quibble about expenses. They need this thing to be perfect. So they're going to spend the money to make it perfect, which means they've got the best tools, the best machines, They keep them in good repair. It's a joy to work in that kind of shop. Like, when you're working to tight tolerances and they don't give you what you need to do the job, it's like a nightmare. But when you're working at tight tolerances and they do give you what you need, then that's like the best work of all, because it's really rewarding. You're getting to, work at the very limits of what is even possible in machining. And all of that support makes it really enjoyable. So that place, highly recommend it. You don't have to have a background in diamond turn machining or micro machining. You have to have a good, solid understanding of the fundamentals, and you have to be very, very curious. Curiosity is the number one thing that they're looking for in people. And that position, Target Fabrication Machinist, is open right now. And I even tried to finagle my way into a job there, and they said no. Very disappointed. But that would
Well,
be it, folks.
okay. Well, that brings us to shop news and new things. You've kind of gone over a lot of the new machinery. If is there any other new things in your program? And if not, please plug the free semester again and where people can go to sign up and all that.
Yeah, we covered so much of it. The Fall is Free program, Fall is Free deal. Anybody can come and take, I think, as many classes as they want during this fall semester, and their tuition fees are waived, and they'll even provide textbooks. So it really is free. It just costs your time. And the one caveat there is that it doesn't apply to international students. But otherwise, so like California residents, who I think are the only people who would be interested in this, all California residents uh, can apply for this. And all you have to do is, you enroll and then you do your FAFSA, your Federal Financial Student Aid application. You don't have to qualify for FAFSA. That's just how they're tracking it. But once you submit that application, you're in. So come in, take whatever classes you want. There's really no excuse now. If you've if you've been wanting to take a class, this is the time. There's no better time.
When's the last day to sign up? Or I guess when does the semester start and then when's the last day to sign up?
So the semester starts on August 22nd, which is 2 weeks from today. We're recording this on the 9th of August. So the 22nd. And you can sign up to the end of the first week of classes. So basically, you have 3 weeks, although earlier is definitely better because it's going to fill up fast.
Awesome. Well, that brings me to the last question I ask every guest every week. And I'm sure you have a numerous amount of things for this question, but what did you research this week? What's been popping up in your browser?
It's been a lot of diamond turning and micro machining, just a lot of that kind of stuff. This is something that I'm just now starting to learn about it in earnest, having a little bit of experience under my belt, and it's just fascinating. It's endlessly fascinating. And if anybody out there wants to go down this rabbit hole, so Cyrus Lloyd in the previous episode mentioned the Society for Precision Engineering, ASPE. If you go to their website, there is a book list. And that book list has some of the best literature I have ever seen. And I had already seen some of them, but there's a lot on there that I hadn't seen. I'm just making my way through it. So if you want to spend a lot of money and a lot of time going down that rabbit hole, highly recommend that you go down that reading list.
Is that because he mentions the competition that they do every year, the student competition. Is that something that you think you might steer your students into in the coming years? Or some of your students, I guess, now that you guys are starting to have more precise manufacturing capabilities?
Potentially, but the competition is more on the engineering side rather than the manufacturing side. I mean, they're interrelated, right? But I think that, first of all, I don't really think that I'd be qualified to. Like, what did he say that the last one was? It was like manufacturing diffraction gratings, and then
Yeah.
the next one was like making an optical profiler. And I'm like, I don't know, man. Like I can make chips. So I don't think we're going to be doing that, but teaching people the fundamentals of ultra precision machining and micro machining, that is something that I'm looking to, because as far as I know, nobody is teaching that. I thought we were the only school, by the way, to have a Kern milling machine. Then I found out that there is somewhere in Belgium, I think it is, there's another career technical education facility that has a Kern. I think it's the same model as ours. And then, of course, there are various universities that have them. But it's very rare for a program like ours to have machines like that. And like I alluded to, there's a possibility that we'll get, the lathe sibling of the Kern machine potentially, and so that would really open a lot of doors. So that's on the horizon.
Okay. Well, Adam, thank you so much for coming on the show. I really appreciate it. Like I said, I had been wanting to get you back on for a while, but you've been so busy, and it's, over the last hour and 40 minutes, it's very clear that you've been incredibly busy, both enabling your program to be that much more effective and, jump into the beyond, and then also personally growing your skills and growing just what you know as precision machining. So thank you so much for taking the time.
Thank you so much for having me. There's so much more that I'd like to talk about, and I will definitely be sharing all of that stuff on Instagram, including I made two like example parts at Livermore Lab during my internship, and that stuff, those are two parts they actually let me take home, and they let me take pictures of them. So I'll be sharing the process and sharing those parts. And I think for people who are looking for practical examples of what we talked about here, that will be very interesting.
That's great. And one more time, what is your Instagram if people want to go find you?
It's Laney Machine Tech, Laney Machine Tech.
Awesome. And it'll be in the show notes. Thank you. Patreon thank yous to Liam, Ethan, and Nate. Thank you guys for backing the podcast. It lets me continue to do episodes like this, talk to amazing people like Adam, and put on the show. And thanks everyone for listening. I'll be back next week.